Hello everyone, this is Dr. Webb. In this video we're really going to be changing gears pretty significantly. We're going to start talking about approximating area under curves. So I thought the best way is to just jump in with an example to talk about how we're going to do this. So here's some curve, and our goal is to figure out what the area under this function is between x equals 1 and to x equals 4. And so when we say under this function, we really mean between the function and the x-axis. So as you can see, this is not some nice geometric shape. You know, we know how to take area of rectangles, triangles, even circles, but generally curves don't give you such nice shapes like that. So how do we do this in general? And so really the first thing we're going to do is we're going to say, well, rather than trying to figure out exactly, let's just try and figure out how we can get a good estimate. Okay, and so looking at this right now, it's a little bit hard to see where places are. So let's put in a nice little grid. So here we've put in a grid. So all of these squares are 1 by 1. So their area is 1. And so looking at this now with these squares on here, it actually makes it not too bad to approximate the area of this, because to some degree we could just kind of count squares, estimate squares that do this. So say, looking at this, you know, between 1 and 2, you know, this little bit up here, triangle there, it looks like maybe it's about the same area as that here. And so I could estimate that area between and those two right there is those two squares. Same thing, that little bit of area right there, I can imagine that's about roughly perhaps the same area as that bit missing in that square there. And so I can maybe estimate the area with those two squares. And so that would give me 3 and 4. And then for this last one, well, it's a little bit hard to, you know, count these. There's definitely a little bit less than it. But I would say total, maybe there's another 2.5 rectangles between 3 and 4. So, you know, if I took that sort of height right there, 2.5, maybe it looks like maybe the area of that rectangle maybe is equal to the area of the yellow region there. And so that would be adding another 2.5. And so I've got 2 rectangles there, plus 2 rectangles there. 2 plus 2 is 4, plus another 2.5. 4 plus 2.5. So that's 6.5. There's a rough estimate on how many on the area of this. And so looking at this, you know, question would be, well, what could we do to make our estimate better? And so in this, we're kind of limited by the size of the squares. So if we made the squares smaller, it might be easier to get a better estimate. So here's the same graph, the same function. All we did is we increased the number of squares. So before, the old squares were 1 by 1. The new squares are 1/2 by 1/2. And so if a square is 1/2 by 1/2, the area of it is going to be 1/4. So if we roughly count the number of squares that it is, and then divide that by 4, that's going to give us perhaps a better estimate for area. So maybe between these two, between 1 and 1.5, maybe that area looks about right. And so that is 3 high. So, or 1, 2, 3, 4, 5, 6. Let's say it's 6 squares, 3 total. Let's erase all of that. So this is, well, it's 3 high. It's 3 by 1/2. Is this rectangle? 3 times 1/2. Maybe for between 1/2 and 2, we say that it's right there. And so this would be 1.5. Yeah. 1.5 by 1/2. Maybe we say the same thing for that one. So that's another 1.5 by 1/2. And so maybe for the height for this one, we'll pick that height right there. So that would be about 2.5 by 1/2. For the next one, well, this is not going to be perfect, but we'll put it right there. And so this is 3 by 1/2. And let's say for this last one, put it right about there. That'll be a decent estimate. And so that's at 2 high by 1/2. And so using these smaller squares, we were able to, break it up into narrower rectangles. And so the area of this rectangle is 3 by 1/2 would be 1.5 plus 1.5 times 1/2. So that's 3/2 plus that. So that's 3/4, which is 0.75. And the next one's the same. And then 2.5, so that is 5/2 times 1/2, so that's plus 1.25. Area of this one is 1, 2, 3, 4, 5, 6 is 1.5, and then the area of the last one is 1, 2, 3, 4. Divided by 4 gives me 1. And so let's see, adding these together, I've got 3 plus 0.7 plus 1, 4.5. So it looks like about 6.75 is this estimate. And because we were using sort of a finer mesh, we'd expect this to be a little bit better estimate than we had before. And we could keep going like this, have even smaller rectangles, break it up even more. Say something like this. For each one, we pick a height that seems to match the area. Maybe for those two, we pick that height right there. Maybe we pick that height there. Maybe we pick that height there. And then if we went and calculated the area of each of these rectangles, added up each of those areas, that would give us about our estimate for this. Okay. So this is going back to the original one, or going back to the one that's 1/4 by 1/4. So let's think about break down really how we're doing this, right? And so really the first thing we did, and this is in terms of the widths that we have here, is that we're picking a width for each area. So let's focus on this right here. So the first thing we did was pick a width. And so this width here is 0.5. This width is in the x direction. And so we're going to call this our delta x. And then above this delta x, we're picking some value to pick the height. And we're trying to get this to, sort of be the approximate area for under the function here. And so kind of what we're doing is we're kind of picking, say, one value of the function on this little interval and picking that to be our height of the function right here, right? And so really here, there is some x value. I'm going to call it xk. And so for the height, we're using the function value there. And so the height there is f of xk. Okay, and so then to get the area for this estimate, well, it's a rectangle, and so our estimated area over this subinterval, this subregion of the graph, well, it's going to be the area of this rectangle. And how do you get the area of a rectangle? Well, it's going to be the base times the height. So the height here is f of xk. Multiply it by delta x. So this is our height. This is our width. Multiply those together. That's going to give us this estimated area here. And then we do that over each of these subintervals, and that's going to give us our total estimate of the area. So for this one, this looks like this is about maybe 1.6. Our width here is 0.5, and so our overall estimate would be about 0.8. And we'd repeat doing this over all of them to get the estimate of the total area. So let's break down how we would do this in general. You know, say if we're just given the function, not necessarily the graph of it, but we still want to break this down using the same kind of logic. So we have the same as before. We have a function. The interval here is we're just giving using points a to b, and we're going to break this into n rectangles, all of the same width along the x-axis. So how exactly would we do this? Well, first we're going to calculate this delta x. So this delta x is talking about the width. And so we're going to have n widths is going to equal the total width. N widths added together is going to equal the total width. And the total width is going from a to b, and so that width is b to a, b minus a. Okay, and so the widths here are delta x. So n times delta x is going to equal b minus a. To solve for delta x, it's going to be b minus a over n. So delta x is equal to b minus a over n. And so this again is going to be the width of each subinterval. Okay, so now that we know how wide each subinterval is, we should find the endpoints of each subinterval. So we're breaking up a to b. So we're thinking about breaking up a to b into n equal widths. And we now know that each of those widths is delta x long. Okay, so this first one, starting at a, is going to go delta x wide. So that's going to be a plus delta x. Next one, we're going to go another delta x wide. So now that's a plus 2 delta x. Another one, we're going to go another delta x wide. So that's going to be a plus 3 delta x. And we're going to keep on doing this all the way across until when we get to the end of the last one, we're going to get at our right endpoint. And so that b is going to be what we get when we go over n delta x's. So all of our endpoints for each subinterval are going to look like this. First one's going to go from a to a plus delta x. Second subinterval goes from a plus delta x to a plus 2 delta x, all the way down the line until the last subinterval ends at b, which is the same as a plus n times delta x. Okay, now we're thinking about some subinterval. So let's say that it's a plus k minus 1 delta x to a plus k delta x. So this would be like the kth subinterval. We have to pick, so our function over here is going like that. If we pick it small enough, if our delta x is small enough, the function is really not going to change very much between there. And so we can just kind of pick some height, being value of the function somewhere, and that's going to be the height of our subinterval. And so the point that we pick to take the function value, we're going to call that x sub k star. And so then the height of this rectangle there is going to be what we get when we plug x sub k star into f. Okay. And so there's lots of different ways that we can pick it. I've been sort of just picking it kind of ad hoc. You could come up with very systematic ways of doing it. And so, yeah, so our heights are going to look like this. And so the question here is, how do we pick these xk stars? So the short answer is it doesn't really matter so long as it's in the interval. The longer answer is you can kind of choose any way that you want to. And so some commonly picked ones is for each subinterval you can always pick the left endpoint. Or for each subinterval you can always pick the right endpoint. Or for each subinterval you can always pick the middle. So the nice thing about the left endpoints and the right endpoints is you already have figured out the values there in the last step. So you know what the endpoints of each subinterval is. For the midpoint, you actually have to, between those, pick the halfway point in between. But again, you don't have to do it this way, although most of the problems will tell you one way to do it rather than another. Another thing you can do is you can just pick them randomly. That's something that actually people often program into computers to do to get estimates. You can always pick the highest point. You can always pick the lowest point. You can always pick halfway between the highest point and the lowest point. It really doesn't matter. Okay. And so now that we have our width, which is delta x, and we have our height, which is the value of the function at that point, well, we picked rectangles because they're easy to get areas of. You just take the width and the height and multiply them together. And so the area of each rectangle is just going to be f of x k star. So the value of the function, this is the height, times delta x. This is the width. That gives us our area of our subrectangle. And then last but not least, to get the total area, to get our estimate for the total area, we're just going to add all of these together. Okay, so we break it up into little rectangles. All of this is we're finding area of little rectangles. And then this last step is adding the areas together. Okay, so let's do this as an example. So here's our function, 8 plus 3x minus x squared. We're doing it between 2 to 4, and we're going to use the midpoints of 3 rectangles. So first thing we got to do is we've got from 2 to 4, and we want to break this up into 3 even bits. Right? So our delta x here is going to be the difference between the endpoints, so 4 minus 2, divided by the number of rectangles that we're doing. So 4 minus 2 divided by 3, each one's going to be 2/3 wide. Right? So our endpoints are going to be 2, 2 and 2/3, add 2/3 again, I get 1 1/3, and then the last one is going to end up at 4. Okay. Okay, so we have each of our sub intervals. They're all going to be 2/3 wide. So now we got to get the heights of each one. So it's telling us to use the midpoints. So we got to get halfway in between each of these. So If the whole way across is 2/3, halfway across is going to be 1/3 over. So this one's going to be at 2 1/3. This one halfway between 3 2/3 and 3 1/3 is just 3. And this last one is going to be at 3 2/3. Okay, so for this rectangle here, it's going to be f, that's not what I wanted to press, f of 2 1/3 times delta x. And then this one is going to be f of 3 times delta x. And this last one's going to be f of 3 2/3 times delta x. So if I plug these into the function, I'm using my calculator while doing this, so it's going to be 8 plus 3 times 2 1/3 is 7/3 minus 7/3 squared. And so this is giving me 9.556, and then I have to multiply it by delta x, which is 2/3. And so I get the area for the subrectangle to be 6.37. Okay, for the next one, doing the function value at 3, so 8 plus 3 times 3 minus 9, that is exactly 8 times 2/3. Eight times 2/3 is 5.33, going on forever. And then last but not least, 3 2/3. So 8 plus 3 times 3 2/3 is 11/3 minus 11/3 squared. So this one is 5.556, and then multiplied by 2/3 for the delta x. So I get about 3.70. So those are my three rectangles. So then to get my total estimate, we're going to add them together. So 6.37 plus 5.33 plus 3.70, and that gives us 5.33 plus 3.7 gives me 15.4. And so that's our estimate for the area. Okay, so for the practice problems for this video, which we'll go over on Wednesday morning, so we've got three area problems. We've got three different functions, each using different ways of looking at the endpoints, either left endpoints or midpoints or right endpoints, and each using a different number of rectangles. So just follow the same idea we did for the last example for each of these, and then we will go over that on Wednesday. So I will, before turning this off, I will leave this up for another second or so. I guess probably you should pause this to get a better look at them. I hope you paused already, and I will see you Wednesday morning. Bye.